Good morning, viewers. I am Dr. Kusumdeep, Professor at the Department of Mathematics, Indian Institute of Technology, Roorkee. I am here to present a course on operation research, which is one of the leading areas of study as well as research. Now, let us see some points about this course. First of all, who should attend this course? So, this course can be attended by UG and PG students, GATE aspirants, UGC CSIR NET aspirants, research scholars and industry personnel. The areas of specialization that would be interested in this course are science, engineering, management, finance and business. Some of the topics that we are going to cover in this course are the linear programming problem and its variants, multi-objective and goal programming problems, transportation and assignment problems, sequencing and scheduling problems and game theory. This course runs over 40 lectures, and as you will see, a number of examples and case studies will be dealt with. Also, from time to time, I will be giving you some exercises based on what we have learnt in the previous lectures. So, this is lecture number 1 on the title as Introduction to OR Models. The outline of this lecture is as follows. First, we will talk about the introduction to the subject of operation research and some definitions. Then we will come to the modeling of real life problems as linear programming problems. We will look at different types of OR models, and finally some question and answers and some exercises. So, what is operation research? Operation research is that branch of mathematics which is used to model and solve real life problems in such a way that an optimum decision is to be made. So, wherever there is a decision making process, the optimization techniques and the operation research techniques come into handy, whether it is a day-to-day activity or some advanced engineering or science or business or financial applications. Now, the operation research has the following sub areas of study. The first one is called the linear programming problems. They are also called the linear optimization problems. Next is the non-linear programming problems or the non-linear optimization problems. Queuing theory is that branch of operation research which studies the queues. For example, when you go to a bank to withdraw your money, you have to follow a queue. Similarly, when you are putting up some jobs on a computer, then a queue is lined up. So, this queuing theory studies the behavior of queues. Reliability theory is also one of the major areas of operation research which studies the reliability of a system, whether it is a mechanical system, whether it is the building, the civil engineering structure of a building and so on. Game theory is another very interesting area of operation research which talks about the decision making process when a game is played between 2 or more than 2 components. The network analysis is that study which talks about the study of the networks. For example, when we have to design a network which is let us say the internet service providers or some other kind of network, it is a study of the network analysis. Then comes the inventory. Inventory control is an important aspect when business has to be dealt with. That is when a commodity has to be stored in some warehouse, and the decision has to be made as to how much quantity of the commodity should be there in the inventory, so that the customers are not lost, and at the same time the cost of storing that commodity is minimized. So, first let us define what do we mean by a optimization problem, because as I said that optimization is the key area of operation research, whether it is network analysis or whether it is queuing analysis, everywhere we encounter the optimization problem. Now, the mathematical definition can be stated as follows: minimize or maximize a function f of x, which is a real valued function defined on the Rn space, that is the n dimensional Euclidean space, and it is a real valued function. So, it is mapped onto the real numbers. X, the capital X is x1, x2, xn is the decision parameters. These are the parameters which have to be determined, and these x values should belong to a set S, where S is a subset of Rn defined by the following conditions: gkx is greater than or equal to 0, where k goes from 1 to up to m. Similarly, hjx is equal to 0, where j goes to 1 to up to l, and ai is less than xi is less than bi, for I goes to 1 to up to n. Now, this f is called as the objective function. That is, this is the function which has to be either maximized or minimized depending upon the problem at hand. Now, the gk's, that is g1x, g2x, they are called the inequality constraints. If they are less than equal to type, then they can be converted to the greater than equal to type. The hjx are called the equality constraints. And these conditions are called the lower and upper bounds, and of course, these x1, x2, each of these x1, x2s, they are called the decision parameters, decision values or decision parameters. These are the ones that have to be determined. Now, in general, all these functions, they are the real valued functions, and they are in general non-linear. So, in general f, gi, hi are non-linear. As a special case, when they are linear, then the problem is called as a linear optimization problem or a linear programming problem. So, first of all, let us look at the various components of an optimization model. The first one is the decision variables. These are the variables that have to be determined for a given problem. As I said in the previous slide, x1, x2, xn, these are the decision parameters, they have to be determined. They are called the decision variables or decision parameters. Second component is the objective function. What is to be minimized or maximized? And the third component are the constraints, that is those conditions which the decision parameters should satisfy. Now, let us look at the various kinds of classification that could exist in the various kinds of optimization problems. The first one is the linear programming problem, which I mentioned earlier. That is those problems in which all the functions involved, that is f, gi, hi, they are all linear. This is the specialized case of a linear programming problem. The second category is called the non-linear programming problems, that is, moment any one of f, gi or hi they are non-linear, then the problem becomes a non-linear optimization problem. Now, it may be possible that the problem does not have any constraints. So, in such a situation the problem is called as a unconstrained optimization problem. However, the moment even a single constraint is imposed on the decision parameters, then it is called as a constraint optimization problem. Then there could be a classification which is based on the type of the decision parameters. What does this mean? The first one is called the dynamic programming problem. This means that the decision variables are dependent upon each other with the help of a particular parameter, usually time. So, that means that they are multi-stage programming problems, and that is the reason why they are called as dynamic, because the decision parameters are dependent on the time factor or some other stage. So, they are called the dynamic programming problems. Then there could be geometric programming problems. In such type of problems, the decision variables could be taking negative powers as well. That is, for example, x1 to the power minus 2, x2 to the power minus 10, like this. So, they are called the geometric programming problems. Then comes the integer programming problems. In these kind of problems, the decision parameters are restricted to take only integer values. They are not allowed to take the real parametric values. Then comes the quadratic programming problems. These are those problems in which the objective function is a quadratic function, whereas the constraints are linear. Then comes the separable programming problems. In such type of problems, the objective function is of the type which is of function of one variable only. That means, let us say f1 of u1 plus f2 of u2, like this. So, the objective function can be broken into a number of terms such that each objective function is of one restricted variable only. Also, we have the stochastic programming problems in which the decision parameters are stochastic in nature. Another classification that exists is based on the objective function. If there are more than one objectives to be minimized or maximized, it is called as a multi-objective optimization problem. In general, a multi-objective optimization problem could be non-linear, and in the specialized case you could also have what is called as a multi-objective linear programming problem. So, both the possibilities exist, that is linear multi-objective and non-linear multi-objective programming problems. Then there are problems in which a particular goal is to be achieved by the objective function, and these are called as the goal programming problems. Also, there could be a situation where a number of levels are to be achieved by the various objectives involved in the objective function. They are called as multi-level programming problems. So, other kind of problems could exist, that is the fuzzy programming problems, in which the decision parameters are fuzzy in nature. Stochastic programming problems in which the decision parameters and the constraints and the objective function are stochastic in nature. Recently, another category of problems and methods has come into existence, which are called as evolutionary computations. These derive their inspiration from living organisms, and in this category we have the genetic algorithms, memetic algorithms, differential evolution, evolutionary strategies. Another category that has come into existence in the last 20 years is the swarm intelligence techniques. These techniques are based on the swarm behavior of a group of living organisms, whether it is a group of birds flying in the sky or some of the fish that are swimming in a pond. Some of these techniques in this category are called the particle swarm optimization, ant colony optimization, bacterial foraging, artificial bee colony, and many more. So, now we will come to the simplest case of the linear programming problem. So, first of all, let us look at the mathematical definition of a linear programming problem. The objective function is a linear function which has to be minimized or maximized. It is of the type C1 x1 plus C2 x2 plus Cn xn. So, as you can see that I have used the x1 and x2 and xn as small. So, the decision parameters are x1, x2, xn, and this could be subject to the following conditions: a11 x1 plus a12 x2 plus a1n xn is less than or equal to b1. Similarly, a21 x1 plus a22 x2 plus a2n xn is less than or equal to b2. am1 x1 plus am2 x2 plus amn xn less than or equal to bm. All the decision parameters xi, they should be greater than or equal to 0, where I goes to 1, 2 up to n. Note that in general m need not be equal to n, and m and n are both positive integers. Also, these parameters aij's, ci's and bj's, they are all real numbers. So, our decision vector x1, x2, xn, this is our decision vector. This has to be determined subject to the conditions that are given in these inequalities. N is called as the size of the problem. Size of the problem. Now, the same definition can be written in terms of matrix notation, that is minimize or maximize subject to minimize or maximize C transpose x subject to Ax is less than or equal to b and x is greater than or equal to 0. Now, let us look at some of the definitions which are related to the linear programming problems. Any vector x satisfying all the constraints of the problem is called as a feasible solution. All those feasible solutions, they combine to become the feasible region. So, the feasible region is defined as the set of all feasible solutions. Out of these feasible solutions, there is one which is called as the optimum solution, and this means that the objective function is the best. So, the best feasible solution is called as the optimum solution. Now, by best we mean either minimum or maximum depending upon the problem at hand. And finally, the value of the objective function at that optimum solution is called the optimum value. So, modeling of real life problems as linear programming problems. Please note that operation research is one such subject which is used to solve real life optimization problems, and that is what we are trying to understand, how real life problems can be modeled as optimization problems, either linear optimization problems or non-linear optimization problems. So, first of all, the case of modeling real life problems as linear programming problems. So, here is an example. It is the maximization of the profit. So, it is called the profit maximization problem. The problem states that a company wishes to produce a product for which it has 3 models to choose from. The labor and the material data for each model is given. Also, the supply of raw material is given to be 200 kgs and the available manpower is given to be 150 hours. We are required to formulate the model so as to determine the daily production such that the profit is maximized. Now, the data that is given in the problem is as follows. There are 3 models A, B and C, and the labor in terms of hours, labor is in terms of hours, it is given per unit. So, per unit of model A requires 7 hours of labor. Similarly, per unit of model B requires 3 units of labor, and similarly the C model, it requires 6 units of 6 hours of labor. The second thing is the materials. So, material is in terms of kg. So, model A requires 4 kg of material, model B requires again 4 kg of material, and model C requires 5 kg of model C. Then comes the profit. The model A per unit has a profit of rupees 4, and for B it is 2 and for C it is 3. So, this is the data that is given in the problem. Now, we will try to model the problem in 3 steps. The first step is identification of the decision variables. So, these are the variables which we have to determine. So, let us assume that we have the following decision variables. X1 is equal to the number of units to be produced of model A. Similarly, X2 is the number of units to be produced of model B, and X3 is the number of units to be produced of model C. These are X1, X2, X3 are the decision variables, and this is what we have to determine. Second step is the identification of the constraints. So, these are the constraints: 7x1 plus 3x2 plus 6x3 is less than or equal to 150. How did this constraint come from? Look at the data that is given to you in the problem. Let me go back to the table. So, here you see in the first row of the table 7, 3 and 6, these are the coefficients of each unit of model A, model B and model C. So, since we have assumed x1 to be a variable, that is the number of units to be produced of model A. So, 7 has to be multiplied by x1, and similarly 3 has to be multiplied by x2 and 6 has to be multiplied by x3, and all of them together when you add them up, this should satisfy the condition, that is they should be less than or equal to 150. Why 150? Because in the problem it is given that there are 150 hours of labor which is available. So, therefore, the sum of all these 3 terms should be less than or equal to 150. In the similar manner, we have the second constraint, that is 4x1 plus 4x2 plus 5x3 should be less than or equal to 200. And of course, all the decision variables x1, x2, x3 should be greater than or equal to 0 and they should be integers. Of course, the value of I goes from 1, 2 up to 3. Why they have to be integers? Because you can produce either 6 units of model A or you can produce 7 units of model A. You cannot produce 6.5 units of model A. That is the reason why this integer requirement is important. The third step is the identification of the objective function. That means, what is it that we have to minimize or maximize. So, here we find in our case the profit has to be maximized, and what is the expression for the profit? It is given by 4x1 plus 2x2 plus 3x3. Why did this come from? Because in the last row of the table you can see in the table that is given, this is the last row, profit in terms of rupees, that is 1 unit of model A requires 4 rupees. Similarly, 1 unit of B requires 2 units, and similarly 1 unit of model C requires 3 units. So, 4x1 plus 2x2 plus 3x3, this is the expression for the profit, and obviously it is common sense that the profit has to be maximized. So, you have to take a decision what you have to do with the objective function, whether it has to be maximized or minimized depending upon the problem at hand. So, therefore, these are the decision parameters in step number 1, and step number 2 we have identified the constraints, and in step number 3 we have identified the objective function which has to be maximized in this case. So, this is the way that using these 3 steps you can model a given problem into a linear programming problem, which is also called as the linear optimization problem. Second problem is regarding the work scheduling problem. These kind of problems have lots of applications, whether it is the scheduling of the workers, scheduling of the nurses, or scheduling of any kind of staff. So, in this problem there is a post office which requires different number of full time employees on different days of the week. The daily requirement is given in the table below, and the union rules state that each full time employee must work for 5 consecutive days and then take 2 days off. That is, the union rule says that there should be 5 days working. We are required to formulate the problem as an LPP so that the post office can minimize the number of full time employees who should be hired. So, let us look at the data that is given. The data says that the 7 days of the week has the following requirement of number of full time employees. So, first of all, if you call Monday as number 1 day, then it requires 17 number of full time employees for Monday. Similarly, for the day 2, that is Tuesday, there are 13 full time employees that are required, and like this for the remaining days of the week. This is the data, this is given in the problem. So, first step is identification of the decision variables. So, it is very simple, just define xi to be the number of employees beginning their work on day number I. So, x1, x2, x3, x7 till x7, these are the number of full time employees that should be employed on each of the 7 days. Of course, all the xi's should be greater than or equal to 0, because you cannot talk about -10 number of employees. So, they have to be greater than or equal to 0, and also there should be integers, because you can either employ 5 employees or you can employ 6 employees. So, therefore, integer restriction has to be imposed. Then comes the objective function. Now, the objective function is the sum of all the employees that have to be employed on all the 7 days, that is x1, x2, x3 up to x7, and this has to be minimized, because the more you employ the more cost is incurred. So, therefore, one is interested in only minimizing the total number of employees. Then comes the constraints. Now, for each of the 7 days of the week we have these constraints: x1 plus x4 plus x5 plus x6 plus x7 is greater than or equal to 17. You will ask why I have not written x2 and x3 in the first equation. In the first equation x2 and x3 are missing, because these x2 and x3 employees, they have to take 2 days off. Okay. So, therefore, during the taking care of the union rules, these number of employees have to be removed from the first equation, and like this for the second equation we have to remove x3 and x4, and like this. Of course, the permutation could be interchanged depending upon the way one tries to model and define x1, x2, etc. So, like this, these are the constraints, and as you know that there are 7 days, so there are 7 constraints. The third problem is about the industrial problem. It says that a company has 3 operational departments. These departments are called the weaving, processing and packaging, with the capacity to produce 3 different types of clothes, which are called as suiting, shirting and woolen, yielding a profit of rupees 2, rupees 4 and rupees 3 per meter respectively. 1 meter suiting requires 3 minutes in weaving, 2 minutes in processing and 1 minute in packing. Similarly, 1 minute of shirting requires 2 minutes in weaving, 1 minute in processing and 3 minutes in packing, while 1 meter of woolen requires 3 minutes in each department. In a week, total run time of each department is given to be 60, 40 and 80 hours of weaving, processing and packing department respectively. We are required to formulate the problem as a LPP to find the product in such a way that the profit is maximized. So, the first thing is, let us tabulate the given information in the form of this table. So, there are 3 types of cloths that are available: suiting, shirting and woolen, and 3 types of processing, that is the weaving, the processing and the packaging. Also the profit in terms of each unit, and also on the right hand side is the available time, that is in terms of hours. So, since we have to take care of the units, some data is given in terms of minutes and the available time is given in terms of hours. So, hours should be converted into minutes in order to take care of the dimension of the data. So, we have 3, 4, 3 in the first row, and this is less than or equal to 3600. So, I think you are now fairly comfortable in guessing how we will define the decision parameters. We will define the decision parameters as follows. Let x1 be the number of units in terms of meters for the suiting cloth, x2 be the number of units of shirting and x3 be the number of units of woolen, and we have to maximize the profit, that is 2x1 plus 4x2 plus 3x3. So, this is the data that is given. So, profit 2x1 plus 4x2 plus 3x3, and also the constraints that are given are as follows: 3x1 plus 4x2 plus 3x3 less than or equal to 3600, and similarly the other constraints 2x1 plus x2 plus 3x3 less than or equal to 2400, x1 plus 3x2 plus 3x3 is less than or equal to 4800, and of course x1, x2, x3 they should all be greater than or equal to 0. Please note that in this particular problem we need not impose the integer requirement, because x1, x2 is the number of units, and that number of units of a cloth, it could be fractional also. That is, you could have either 2 meters, or you could have 3 meters, or you could even have 2.34 meters, or you could have 2.5 meters as well. So, therefore, the integer requirement is not necessary in this particular example. Another interesting applications is about the advertising. Now, the owner of a win-win sports company wishes to determine how many advertisements to place in the monthly magazines A, B and C. His objective is to advertise in such a way that the total exposure to the principal buyers of the expensive sports good is maximized. The percentage of readers of each magazines is known, and also the exposure in any particular magazine is the number of advertisements placed in that magazine multiplied by the number of principal buyers, and this information can be recorded in this table, that is magazine A, magazine B and magazine C. The readers, how many readers are there? Magazine A has 1 lakh readers, magazine B has 0.6 lakh readers and magazine C has 0.4 lakh readers. And the principal buyers are 20%, 15% and 8% for the 3 magazines A, B and C. Also the cost per advertisement in terms of rupees is given to be 8,000, 6,000 and 5,000 for each of the 3 magazines A, B and C. Now, the budget amount is at most rupees 1 lakh for the advertisement, and the owner has already decided that magazine A should have no more than 15 advertisements and that the B and C magazines have at least 80 advertisements. So, we are required to formulate the given problem as a linear programming problem. So, let us first of all define the decision parameters. Let x1, x2 and x3 be the number of insertions in the magazines A, B and C respectively, and the objective function can be written as follows, which is nothing but the total exposure, that is how many people are going to read it. So, we have to maximize the total exposure, and mathematically it can be written as 20% of 1 lakh times x1 plus 15% of 60,000 times x2 plus 8% of 40,000 times x3, and when you simplify this you get the following expression. And the constraints for each of the conditions, that is the budgeting constraint, because the budget is given to be 1 lakh. So, therefore, the budgeting constraint can be written as 8,000 x1 plus 6,000 x2 plus 5,000 x3, which should be less than or equal to 1 lakh. And similarly, the advertising constraint says that the first magazine should have not more than 15 advertisements. So, therefore, x1 should be less than or equal to 15. As far as the B and C magazines are concerned, they must have at least 80 advertisements. So, therefore, x2 should be greater than or equal to 80 and x3 should be greater than or equal to 80. Of course, the decision variables x1, x2, x3 should be greater than or equal to 0 and they should be integers, because you cannot insert 2.5 insertions in advertisements in a magazine. Either you insert 2 or you insert 3. So, therefore, integer restriction is important. The fifth problem is called the portfolio optimization problem. Assume you have inherited rupees 1 lakh from your father that can be invested in two kinds of stock portfolios with the maximum investment allowed in either portfolio set as rupees 75,000. The first portfolio has an average rate of return of 10%, whereas the second has 20%. In terms of risk factors, the first and the second portfolio have a risk rating of 4 and 9 respectively on a scale of 0 to 10. Since you wish to maximize your returns, you will not accept any average rate of return below 12% or a risk factor above 6. Hence, you face the important question, how much you should invest in each portfolio. For this, we will model the problem as a LPP. So, given data can be used to model the problem as follows: maximize 0.x1 plus 0.x2. Of course, x1 and x2 are the amount that you have to invest in both the schemes. Subject to the condition x1 plus x2 is less than or equal to 1 lakh, x1 is less than or equal to 75,000, x2 is less than or equal to 75,000, 0.1 x1 plus 0.2 x2 should be greater than or equal to 0.12 multiplied by x1 plus x2, 4 x1 plus 9 x2 should be less than or equal to 6 times x1 plus x2, and obviously x1 and x2 should be greater than or equal to 0 and they need not be integers. So, I have given you 5 examples to illustrate how we can model real life problems as a linear programming problem. Now, as an exercise, I will give you some questions. The first one is the profit maximization, that is, a company produces 2 types of hats. Each hat of the first type requires twice as much labor as the second hat. If all hats are of the second type only, then the company can produce a total of 500 hats a day. The market limits the daily sales of the first and the second type as 150 and 250 hats. Assuming that the profits per hat are rupees 8 for the first type and rupees 5 for the second type, formulate the problem as a LPP in order to determine the maximum profit. So, I think you can easily model this problem as a LPP by defining the 3 steps that we have learnt in this lecture. Second exercise is about the trim loss. This is a very interesting application and this occurs in all kinds of industries, let us say the paper industry, the textile industry, the glass industry, the steel industry and so on. The problem says that rolls of paper having a fixed length and width of 180 centimeters are being manufactured by a paper mill. These rolls have to be cut so as to satisfy the following demand: obtain an LP to determine the cutting patterns so that the demand is satisfied and wastage is minimum. Now, the data that is given is the width is given in terms of 80 centimeters, 45 centimeters and 27 centimeters, and the number of rolls is 200, 120 and 130. Now, for solving this model, I mean for modeling this problem, here is a hint. You have to try to look at the various alternative cutting patterns. Now, each of the cutting patterns is shown here in this table. For example, I will explain the first one. If the cutting pattern is 80 plus 80, the first one, so the number of rolls that have to be cut, you can define them as x1, x2 etc. and the wastage per unit per roll is let us say 20. This 20 comes from the fact that if you have two types of patterns, that is 80 plus 80. So, 80 plus 80 is 160 and 160 has to be subtracted from 180. So, 180 minus 160 is 20. So, that is the wastage. So, you have two types of 80 centimeter and 0 type of 45 and 27 centimeter. So, like this you have all these cutting patterns, and accordingly based on the decision parameters x1, x2, x3, you can write the model as follows: minimize 20 x1 plus 10 x2 plus x3 plus 19 x4 plus 18 x6 plus 9 x7 plus 18 x9, and subject to these conditions on the 80 centimeter roll, the 45 centimeter roll and the 27 centimeter roll. And of course, there are 9 variables, xi should be greater than or equal to 0. So, in the end I would like to mention some of the books that you could read for getting more information on this topic of operation research, and this is going to help you to study the other lectures in this course as well. The first book is by Chandra Mohan and Kusumdeep. It is called as Optimization Techniques by New Age International India 2009. K.V. Mittal and Chandra Mohan, Optimization Methods in Operation Research and System Analysis. This is also by New Age International. And the third book is by S.S. Rao. It is called Engineering Optimization Theory and Practice. Another book is by Taha, H. Taha. It is Operation Research and Introduction. And finally, S. Sai Gas. This is a book on linear programming. So, with this we come to the end of lecture number 1 of this course. Thank you so much.